I learn science every day. What is science for Monday? A butterfly hatched from its pupa. What is science for Tuesday? I'm served a sprout from the plant. What is science for Wednesday? How do amphibians do today? What is science for Thursday? Amazing Einstein's AMC squared. What is science for Friday? I want to meet Michael Faraday. I learn science every day, except Saturday and Sunday, because it's family day. Hooray! Good morning! I'm Gavin Manala and this is Learn Science Every Day. So for today, we will learn topics from nuclear physics. The specific topics are chain reaction and non-radioactive isotopes. Using Google search engine for you students, learn what to search when you are going to review. First, in the search box, we will type nuclear physics and then click enter. And then we will see the definition of nuclear physics. So by definition, nuclear physics is the physics of atomic nuclei and their interactions, especially in their generation of nuclear energy. Now this means that nuclear physics involves the nuclei or the center of the atoms and how they interact with each other and how they generate nuclear energy. By going to Encyclopedia Britannica, nuclear physics, this is a branch of physics that deals with the structure of the atomic nucleus and the radiation from unstable nuclei. So this means radioactivity comes from an unstable nuclei about 10 times smaller than the atom. The constituent particles of the nucleus, protons and neutrons, attract one another too strongly by the nuclear forces that nuclear energies are approximately 1 million times larger than typical atomic energies. Quantum theory is needed for understanding nuclear structure. Looking back from the basic studies of matter, so matter composes of molecules and then molecules composes of atoms. So these atoms have nucleus that consists of protons and neutrons. So we can only see protons and neutrons in the nucleus. So they attract one another because protons have positive charge and neutrons have no charge at all. Next, we will find out more about radioactive decay. Just type in radioactive decay, then click enter. By definition, radioactive decay is a spontaneous breakdown of an atomic nucleus, resulting in the release of energy and matter from the nucleus. Remember that the radioisotope has unstable nuclei that does not have enough binding energy to hold the nucleus together. This means that there is a standard amount of energy needed to hold the nucleus together. But in the case of a radioactive isotope, radioactive decay happens when the isotope doesn't have enough energy to hold the nucleus together. Again, in the nucleus, we have the proton and neutron. Next, we will move on to the concentrate of this lesson. Nuclear chain reactions. By definition, nuclear chain reactions are series of nuclear fissions, splitting of atomic nuclei. So nuclear fission is splitting of atomic nuclei, each initiated by a neutron produced in a preceding fission. For example, 2.5 neutrons on the average are released by the fission of each uranium-235 nucleus that absorbs a low-energy neutron. Uranium-235 is an example of a radioactive isotope because neutrons are not balanced with the protons. To give you a perfect example of uses of radioactive isotopes, we have here a video of an atomic bomb.
First atomic bomb, called Trinity. Over the next 5 decades,
on July 16, 1945, the United States tested the first atomic bomb, called Trinity. Over the next 5 decades, the country tested more than 200 bombs in the atmosphere. The explosions, called shots, were recorded by dozens of high-speed cameras on film for analysis of the bomb's destructive power. Now, there's a race on.
We also have the nuclear bomb, which is also widely used since 1945. The first country to have used the nuclear bomb is the United States of America since 1945. The next, they used it to bomb Japan. So as you can see, in the passing years, United States of America have used nuclear bombs will give us a clearer idea of how chain reactions happen. Searching from YouTube, we will type chain reactions, nuclear physics.
Enormous energy and 2 or 3 trash neutrons are emitted. If the conditions are favorable, these neutrons take part in the fission. This leads to a chain of nuclear fissions, which continues till the whole of the uranium is consumed. Thus, the energy produced keep on multiplying.
So next we move on non-radioactive isotope. By searching into Google, let's type non-radioactive isotope. By definition, non-radioactive isotopes are stable isotopes and non-radioactive forms of atoms. Although they do not emit radiation, their unique properties enable them to be used in a broad variety of applications, including water and soil management, environmental studies, nutrition assessment studies, and forensics. So these are non-radioactive forms of atoms. So what do we mean by that? So it means it does not emit high energy that results into catastrophic explosions. So they are widely used into non-explosive uses. A perfect example of non-radioactive isotopes in human metabolic research, the most commonly used stable isotopes include hydrogen, carbon, and nitrogen isotopes that can be incorporated into molecules to be used in metabolic tracers. These elements have one or more isotopes with specific natural distribution patterns of abundance. Let's dig into it further. We have here an article about metabolic tracers. So let us summarize the abstract. The human body of stable non-radioactive isotope tracers in vivo human metabolic research. Stable isotope tracers can be used in conjunction with molecular and cellular biology tools, thereby providing an in-depth dynamic assessment of metabolic changes as well as simultaneous investigation of the molecular basis for the observed kinetic responses. The research introduced basic principles of stable isotopic methodology for tracing in vivo kinetics of human or animal metabolism, with example of quantifying certain aspects of in vivo kinetics of carbohydrate, lipid, and protein metabolism. To briefly explain, stable isotopes are used for monitoring metabolism of carbohydrate, lipid, and protein in a human or animal body. In this diagram, we can see how the metabolic tracers like hydrogen, carbon, or nitrogen can be used to monitor protein, lipids, and carbohydrates metabolism. Isotope tracer is a molecule that is chemically and functionally identical to the naturally occurring molecule of interest. This time, the researchers use carbon as a metabolic tracers because they are tracing carbohydrates, lipids, and proteins, which are biomolecules. As a summary, we can conclude that stable isotopes are more abundant than radioactive isotopes. Radioactive isotopes breaks down easily because of unstable nuclei. Thank you for watching. I hope we learned a lot of topics and concepts in physics.